Hello, my name is Ruturaj Sambus. I am presenting our work at the Trek Lab, Virginia Tech, titled Real-Time Model-Free Deep Reinforcement Learning for Force Control of a Series Elastic Actuator. This work showcases the successful training of a model-free deep reinforcement learning policy for force control of a hardware series elastic actuator driving a pendulum. Safety mechanisms are developed for training the policy for over 21 hours without an operator. The policy demonstrates enhanced tracking and stability compared to a conventional model-free PID controller. Model-free PID methods face challenges with nonlinearities. Common model-based approaches from the literature, such as disturbance observer and adaptive control methods, demand significant effort to acquire system knowledge through meticulous system identification techniques. Model-free DRL methods have predominantly been employed for position-based trajectory tracking trained in simulations, with only a few works exploring hardware learning. While DRL policies often transfer well to high-end robots trained on simulators, their application becomes challenging for custom hardware under development without an accurate model available. Learning on hardware is our key focus for multiple reasons. Firstly, the considered SEA exhibits complex, unknown nonlinearities that are challenging to precisely model. Creating a simulator that accurately accounts for these complexities would require substantial time. Secondly, attempts to fine-tune a model-free PID controller often resulted in system instability or unresponsiveness. We formulate the reinforcement learning problem with a reference force trajectory being a 50 Newton sinusoid with frequency randomly sampled from 0.05 to 0.35 Hz. The reward is proportional to the square of tracking error. The state is a 5-dimensional vector encompassing joint position, velocity, acceleration, and force. The action space is one-dimensional, being the applied current. The learning policy is queried to get a new action at the frequency of 100 Hz. The experimental hardware consists of a Maxon EC motor belt driving a THK ball screw via a geared transmission. This work utilizes sensing modalities of an inline force sensor and an absolute joint encoder. The low-level controller, composed of a networking shield, a microcontroller, and a sensor interface shield, communicates with the networking PC at a frequency of 400 Hz. We have developed a comprehensive framework consisting of 6 layers of safety mechanisms, ensuring uninterrupted, secure, and autonomous hardware learning. Alongside a physical emergency stop switch, the low-level controller incorporates an automatic emergency stop feature based on joint position and actuator force limits, effectively preventing any potential damage to the system. A learning boundary determined by position limits is established. Beyond this boundary, an opposing constant current is automatically applied to guide the pendulum back within its safe operational range. This feature played a crucial role in the successful policy learning process. The PPO policy exhibited a remarkable reduction of 25 Newton, that is 63% in the mean absolute error for 50 Newton sinusoidal trajectory at 0.1 Hz. There was an 87% enhancement in the average episodic reward across 4 experiments. Moreover, the paper discusses the significance of learning rate decay as well as a heuristic based on 90-minute intervals combined with the monitoring of KL divergence and entropy plots to prune experiments. Tuning the PID controller often resulted in oscillatory behavior. Consequently, a 1 Hz low-pass filter was necessary for stable control. Interestingly, DRL controller consistently exhibited stability across 150 hours of experimentation. Although tracking error increased with frequency for both the controllers, DRL showcased lower absolute error compared to PID for frequencies above 0.15 Hz as depicted in the plots. Thank you for your time. Please refer to the paper for more details.